All right, we're on the last section in this cycle. This one is about exponential functions, which is a little bit of a struggle, I think, for some at first. It's not too bad once you start to get the hang of it and understand each part of the exponential function. Just like the linear function equation is y equals mx plus b. Once you kind of have what m is and what b is figured out, your slope and your y-intercept, they're not too bad. Same thing for these exponential functions. They just look scary because they have an exponent and sometimes they have fractions thrown in there. So the important thing to remember is that exponential functions have the form y equals the starting value, which is your y-intercept, times the multiplier, which is how kind of like your rate of change, how you get from one point to the next, and then to the power x. So I think the easiest way to do this, just showing you on this recording here, is to just kind of do a few, and hopefully you catch on as I do the first couple of problems. So I'm going to take this first graph and do it that way. Instead of going A, B, C, D, I'm going to go 1, 2, 3, 4 for the graphs. Okay, so this graph just goes with the equation C. Y equals 7 times 2 to the power x. Now, how did I know that? Well, if I look at the y-intercept, which is my starting value for this graph, it's 7. Okay, my function is crossing the y-axis at 7. Okay, and then my multiplier is times 2. Okay, how did I know that? Well, I can find nice points and see, okay, so from this point to this point, I increased by multiplying by 2. I'm also increasing. If I have a whole number, my function is increasing. Okay, let's go to the next one. We notice that this one is decreasing. The function for that will be y equals 1/4 to the power x. Now, this isn't a starting value times a multiplier. Why? Well, if I look at my y-intercept, it's at 1. And typically, we don't say 1 times 2 or 1 times 3. It's just implied that we're multiplying by 1 if it just says 3. We don't actually have to write it. So in this case, they did not write the starting value. It's implied that it's 1. Okay, then my multiplier is 1/4, meaning that to get from one number to the next number on the x's, I'm dividing by 4. So this function is decreasing. So notice here, to get from one x value to the next x value, I had to multiply by 2, meaning that my numbers are going to be increasing. Here, I'm dividing by 4 or multiplying by 1/4, so my numbers are getting smaller each time. So decreasing. All right, if you want to go ahead and try 3 and 4 on your own, you can absolutely pause the video now. There's only 2 possible answers left. Maybe you can match them up if you want to try, otherwise I'm just going to keep going. So for this one, the function is y equals 10 times 3 to the x power. Why is that? Well, 10 is my y-intercept, and to get from one x value to the next x value, I'm multiplying by 3, and my function is increasing. The last one, my function is y equals 6 times 1/3 to the power x, where 6 is my y-intercept, and my multiplier is 1/3. This function is decreasing. So for all of these ones, I think the easiest thing to identify is the y-intercept because they all happened at like perfect, nice whole number points. A little bit harder to see the multiplier, especially with such a small graph. It's kind of hard to see, oh, I'm multiplying by 3 here, or I'm dividing by 3 here. So definitely look at the y-intercept first. I think that's going to be the easiest route, especially for these problems here. Okay, number 2. Where does the starting value in the exponential function appear on the graph? I've said this multiple times. It's the y-coordinate of the y-intercept. So your starting value is the same thing as your y-intercept. And then part B, describe the value of the multiplier when the y values on the graph are increasing, and then describe that value of the multiplier when the graph is decreasing. So I kind of mentioned it a couple times before, looking at our two increasing functions here, what does the value of my multiplier look like? And then for my two I can't scroll over anymore, but my two decreasing functions, what does my multiplier look like? Well, when I'm increasing, we have whole numbers, so 2 and 3, and when I'm decreasing, I have fractional numbers. So to put that into words, when my exponential function is increasing, we have a positive multiplier greater than 1, and decreasing exponential functions have a positive multiplier less than 1. That less than 1 is just signifying that it's a fraction. We're not going to see these fractions being larger than 1 in this case right now. All right, moving on. If you want to see some more notes, you can go ahead and read through this part. Some vocab words for you where they kind of put it into a different perspective if you want to look through their explanations and their examples. Go ahead. Notice in this one, it's not a fractional multiplier, it's a decimal. So that's why in the example I said less than 1, because I didn't want to put it's a fraction, because, well, in here it's not a fraction, it's a decimal, and it's less than 1. And notice that it's decreasing. Here, the multiplier was 5, so a number greater than 1, and it's increasing. Moving on to number 3. Remember that we can interpret the multiplier to understand the rate of change in an exponential function. So multiplier is just the rate of change. Multipliers that are whole numbers like 2 or 3 indicate that the y value is doubling or tripling. They can also be interpreted as a percent. For example, the multiplier of 2 is the same thing as multiplying by 200%, or multiplying by 200%, or increasing by 100%. If the multiplier is a decimal, then the rate of change is often interpreted as a percent. So for these ones, suppose y is an exponential function of x that has an initial value of 7 and a 10% growth rate. Write the function for y. So I'm just writing their function. This percent I'm going to need to write as a decimal. And remember, when I'm doing this, it's always 1 plus the decimal, or 1 plus the percent amount written as a decimal. So thinking back to last semester, we talked about that as a growth or decay rate. So for this one, my starting value is 7, and my growth rate is 10%. So 1 plus 0.1 gives me that 1.1 to the power x. Okay, then suppose same kind of stipulations. Initial value of 7, this time 10% decay rate. So instead of 1 plus the 10%, I'm going to go 1 minus that 10%. So I'll have y equals 7 times 0.9 to the x power. And then for this last one here, number 4, oh, no, we're going to do 5. So for number 4, for each exponential function, state the following and then graph the function. So we've got a lot of things that they want us to list in graphing the function. So we need to first say if the function represents exponential growth or decay, if the function is increasing or decreasing, the starting value, the multiplier, the rate of change, and 2 points on the graph. Okay, I just left the graphs graphed when I was going through this, but looking at this function, can we tell if it's a growth or decay? Similarly, is it going to be increasing or decreasing? So I'm looking at my multiplier, which is that the 1.1. It's a number larger than 1. So we know that it's increasing, meaning that we have a growth. So it's growing, it's increasing. Those are kind of linked together. What's the starting value going to be? Well, my starting value is going to be, I'll just leave it here. Starting value is going to be 8. The multiplier is going to be the 1.1. My growth rate, or my rate of change, or my growth rate is going to be 10%. So thinking back to this one here, they had a multiplier of 1.1, meaning that it had a growth rate of 10%. And then what's the next point? They asked for 2 points on the graph. So in order to figure that out, I can always just go to Desmos here and plug in 2 x values. So I have 8 times 1.1 to the power, let's say 0. Okay, so then my first point would be 0,8. And what if I did it for 1? Then it would be 8.8. Okay, you can use those 2 points right here in order to graph your function. And then just, I know mine looks absolutely terrible, but we can kind of get the gist that it's increasing. Okay, and then the next one, same thing. We're looking at our multiplier to decide if it's increasing or decreasing, if we have a growth or decay. And for this one, it's 1/2. So that's a number less than 1. So I'm going to be decaying or decreasing my function. My starting value is going to be at 5. The multiplier is 1/2 or 0.5. So my rate of decay, my decrease rate is 50%. And for those 2 points, I can do the exact same thing that I just did. 5 times 1/2, to the power 0, I'd get 0,5. And if I plugged in 1, I'd get 1,2.5, or if you want it as a fraction, it would be 5/2. All right, and then now we're moving on to the last one. Number 5, Candy Crush Saga is a popular app in which color candies are matched. Super fun game. The app is free to download, but requires purchases at certain points to advance in the game. It also offers in-app purchases to progress faster in the game. So if you are wanting to cheat, you can pay your way to cheat through it. Although it's not really cheating, but I think it's cheating. I never pay for it. Anyway, 1 year after its debut, it had been downloaded more than 500 million times. If you don't believe me, you can go to company.king.com to check it out yourself. Okay, in a recent month, the app brought in $43 million in revenue after Google and Apple took 30% of its revenue. How much revenue did the app earn before paying Apple and Google? Okay, so for this one, I'm going to use my exponential function equation, y equals the starting value times the percent increase or decrease, so my rate of change, to the power x. I don't know what my starting value is because they're asking me what my starting value is, but I do know the ending value. So that 43 is my ending value after 30% was taken out. The x value represents my starting value. That's what I'm trying to find. And then this 0.7 is 1 minus 0.3, which is meaning that they lost 30% of their revenue because they had to pay Apple and Google. So then I'm just basically solving for x here, meaning that Candy Crush in 1 month made $61.4 million. Part B, if the app has been downloaded 500 million times already and gains 8 million new downloads per month, write a linear model of the form y equals mx plus b to represent the number of downloads. We're going to use D for the number of downloads in millions and M for the number of months. So I'm kind of using literal equations here instead of using X and Y. D is for downloads, M is for months. So Y equals MX plus B. Downloads equals 500 million times already downloaded plus plus 8 million new downloads per month. And yes, I know that doesn't really follow the form y equals mx plus b. So if you're really picky, you can rewrite it as d equals 8m plus 500. Same exact thing. I just wrote it this way because that's how I read it, that they already had 500 million and then they gained 8 million per month. But either way, doesn't matter. Part C, if the app has been downloaded 500 million times already and the number of downloads grows by 2% each month, write an exponential model of the form y equals a times b to the power x. A, remember, is your starting value, and B is your growth. To represent the number of downloads, we're going to use those same variables. So D equals my starting value, which was 500, and then times the 2%. How did I get that? It's just 1 plus the rate. So 0.02 plus 1, that's where I got that, and then to the power m. So from here, in order to figure out how long it'll take me to reach 1 billion downloads, I'm not going to plug in 1 billion downloads. I mean, I could plug it in for D and solve for M. I think it's just a little bit easier to use Desmos. I don't actually have to do any math. So I'm going to go to Desmos. I'll type in my linear model, which is 500 plus 8m, which is really x. Okay, then there we go. Here I am. Now I want to figure out when D or Y equals 1 billion. And remember, we're in terms of millions. So my Y value is going to need to be 1,000. And then I can scroll up to where Y equals 1,000 and see where it intersects my graph. So here, my linear model, it says it's going to take me 62.5 months, which if you want me to convert that to years, just so you can get like a better sense, it's 5 years and 2.5 months. Now for my exponential equation, I'm going to go 500 times 1.02 to the power x. And let's see if that was graphed. Yep. It's this red line, and I already have y equals 1,000, so I'm just going to scroll over. Oh, no wonder it's a little off. To the power x. Okay. I was wondering why it was so far off. Okay, that's better. Otherwise, it was saying it was going to take 1 month, and I knew that was definitely wrong. Okay, so I just tap on the point, and it looks like it's going to take pretty much just a straight up 35 months to download 1 billion times, or if you want to convert that, it's 2 years and 11 months. All right, so go ahead and you can start your homework section.